Hi everyone, my name is Vikul Kumar. My roll number is 2011CS24. My team has two of my friend Asutosh Abhishek, whose roll number is 2111CS23, and Trikjin, whose roll number is 2111CS11. Our deep learning survey project is road traffic forecasting, recent, advanced, and new challenges. Introduction. Traffic forecasting begins with the collection of data on current traffic. This traffic data is combined with other unknown data such as population, employment, trip rates, travel cost, etc. to develop a traffic demand model for the current situation. With the rapid urban growth, traffic problems such as congestion, traffic accident, and air pollution have become the constraints of economic development and the bottleneck of social progress in the world. Fortunately, Intelligent Transportation System (ITC) can be help people to solve this issue by processing large amount of traffic data to provide a traffic control route guidance, road conditional warning, etc. Among these applications, accurate traffic flow prediction is pre- prescribed of the implementation which can provide a convenience for the traffic management, improve public travel quality, relieve road congestion, and reduce the accident rate. Traffic flow is defined as the total number of vehicles passing over a given section or point of a road during a given time interval. The prediction of a traffic flow has a long history in ITS, attracting numerous attractions from worldwide researchers. In general, there are two very effective models in traffic flow prediction. First one is statistical model, which focus on imaging and forecasting at a single point based on temporal and spatial serial spatial series from historical data of traffic flow, such as auto-aggressive integrated moving average model (ARIMA), Kalman filter, Gray theory, and Stokes model. Second one is intelligent computational model represented by neural network, Bayesian network, fuzzy and inventory technique has have obtained remarkable achievement in traffic prediction. In recent years, deep learning has been paid more attention to establish traffic flow prediction model by using deep neural network which can perform better multiple representation and abstraction which less prior knowledge. Abstract accurate traffic flow prediction is the precondition for many applications in intelligent transportation systems such as traffic control and route guidance. CNN-based multi-feature predictive model MFCNN that collected the predicts network scale traffic flow with multiple spe- spectral feature and external factors, weather and holidays. Intelligent transportation system ITS in which several areas such as vehicular perception and traffic analysis have widely embedded deep learning as a core modeling technology. In short term, in short term traffic forecasting, the capability of a deep learning to deliver good results has generated or prevented inertia towards using deep learning models.
Aimed at the traffic prediction of a single road, it might ignore the part of the spatial features and the temporal features in a traffic network, which are more effective and practical for understanding of the traffic flow. It shouldn't be neglected, it should be paid more attention. So our primary consideration is how to extract the spatial and the temporal features of a features efficiently. So here comes the convolutional neural networks. As it preserves the neural neighborhood relation and spatial locality, CNN. So here is because it preserves the neighborhood relation and spatial locality. CNN and a deep residual network to predict the citywide crowd flows, CNN to predict the traffic speed, spatiotemporal recurrent convolutional neural network to predict the traffic speed of urban roads, tends to prove that the CNN is pretty effective in this field. So one of the most prominent method that is traffic flow prediction using the convolutional neural network and a multi-feature fusion. Traditional data-driven traffic flow predictions suffer from the shift brought by the various complex factors such as weathers and holidays. It also tends to ignore the traffic sub-features such as daily periodicities and weekly periodicities. And in a time dimension, traffic flow prediction not only depends on the temporal continuity, it also depends on the daily periodicity, weekly periodicity, space neighbor, weekly periodicity, and a space dimension. It not only depends on the neighborhood roads, it depends upon the faraway roads too. And also the external features such as weather and holidays affect the traffic flow predictions very greatly. The dataset for this given model is collected from the Chilean Provisional Expressway Administration from China, Caltrans Performance Measurement System from USA. This dataset consists of 20,352 samples if on 18 road sections collected over the 1st January 2017 to 31st July 2017 within a time interval of 15 minutes. Similarly, the PMS data is also collected. It also includes the external factors such as weather conditions, temperatures, wind power, holiday, weekends, etc. Now, let's talk about the tempo, about some graphs. Here, the figure A shows that the one-day traffic flow from 12 p.m. to 4 p.m. at the time interval of 15 minutes. On the graph B, it shows that the traffic flow from of a 1 week traffic flow of a 1 week, and it also shows the daily periodicity. It also shows the daily periodicities here. Here it is clearly also visible. And the figure C shows that the traffic flow of at a given time on a Wednesday of each week from March 1 to July 19. Here we also see the weekly periodicities, and in a May on a May month of May we see a local peak because it is because of an international workers holiday, and in the month of June and July we see that there's a fluctuations because the temperature was rising. Sorry. In general, overall trend is rising in all these three, thus validating that the traffic self features in a trophy, temporal continuity and daily periodicity and weekly periodicity, which greatly influence the traffic flow predictions. On the right side figures, it shows the impacts of external factors on traffic flow. Figure A shows the weather conditions effects, that is like one is collected on a stormy day and other is on a sunny day. It is shows that there's a great changes. And on the figure B shows uh, traffic flow effects, traffic flow trends on a ordinary day and an international worker day. Here also there's a huge differences. Now preparing the dataset. Our dataset consists of a three spatio-temporal data, that is temporal continuity, daily periodicity, weekly periodicity. Each of these data consists of sorry. Here in a here each of these input matrices is a two-dimension matrices, and then where T denotes the time and P denotes the locations. Here the 94 means the number of vehicles at the location 2 at the given time t minus 2. Similarly, the daily periodicities and weekly periodicities are calculated, are mentioned. So our model consists of two parts. One is three types of spatial transformation, spatial temporal features, and second is the external factor, sorry, external factors and spatial temporal features. Unlike the raw images, where several pixels represent the similar features or input matrix for the traffic flow, for each pixel it holds the real meaning of the traffic flow. So several so the several studies shows that subsampling of such matrices several studies show the subsampling of such matrices is not gonna prove better. It tends to show the accuracy loss. So in this model, the author is not using a pooling layers and it only using a consecutive successive convolutional layers. This model consists of a two-dimensional convolutional neural networks to find the spatial temporal features. By convolutional models, we get three sets of high-level features. These extracted features will be flattened into the fixed dimensional vectors, and also the external factors are also flattened into the fixed dimensional vector. And uh, these two vectors are then merged together by using a logistic regressions, which is by which we can find the predictions. Okay, now let's talk about the analysis of a combination of our various features. Authors de authors deploy a few models, that is like temporal model depend on a temporal continuity, Delhi periodicity, weekly periodicity, and external factor combinations. Here we observe that the models with the combinations of CND and CNW performs better than the models which only depends on a temporal continuity. And also we observe that the models with the combinations of all the features along with the external factor performs greatly better than the other models, above models. Also, the authors compare this model with the five base layer models, that is artificial neural network, stacked autoencoder, convolutional neural network, long short-term memory, and convolutional long short-term memory. It is observed that on a JPA dataset, the author's preferred model is performing a lot better than all the above five base models. But on the PMS model, but on the PMS dataset, it is observed that the CLSTM is performing a bit better than the multi-features convolutional neural network. It is because that the multi-feature convolutional neural network depends only on the CNN capability of extracting the features, whereas the CLSTM depends on CNN and LSTM both. But the training complexity of the CLSTM is very harder, and it is observed that the runtime complexity of the MFCNN is way better than a CLSTM. It is almost like half of the CLSTM runtime. Here from this graph we can observe that MFCNN runtime is pretty lower and pretty good, better than the CLSTM.
Hello everyone. So, as it has already been discussed by Vicolo and Rixin, we know that the recent advances in location acquisition and wireless communication technologies have led to a very wide availability of spatio-temporal data, which has some unique spatial properties and some unique temporal properties. So, like spatial properties, there is some geographical hierarchical structure in the data, and there is a sense of distance in data. In terms of temporal properties, we see that the data has closeness, it has periodicity, and some trend as well. So, the spatial temporal data is inherently different from text and image data in many senses. For example, we can say in context of spatial properties, for example, locations are at a higher level of geographical hierarchy, and if the locations are at a higher level of geographical hierarchy, they have a coarser granularity, and the territory of a parent node is composed of those of its children. Say, for example, a tourist attraction is located in a district which might further belong to a different city. So, there is also a sense of geographical distance between two locations which can measure the correlation between them. For instance, near locations are considered more similar than distant ones. So, in context of temporal properties, for example, the timestamp of each instance in a spatiotemporal dataset allows us to order instances chronologically, generating sequential properties where adjacent timestamps usually are at a higher similarity than distant ones. Likewise, spatiotemporal data usually has a certain periodic pattern which repeats with a certain frequency. For example, traffic conditions during morning rush hours may be similar on consecutive workdays, repeating every 24 hours. So the model that is being proposed here is called DeepST. It comprises of two components. One is spatiotemporal component and another one is global component. The spatiotemporal component employs the framework of convolution neural networks to simultaneously model spatial data and distant dependencies and temporal closeness, period, and trend in the data. The global component is used to capture global factors such as the day of the week, the weekday, or the weekend. So DeepST proposes a deep learning architecture for spatio-temporal data and using domain knowledge, and proposes employing temporal properties to select appropriate timestamps for modeling temporal closeness, period, and trend. And it also proposes the use of convolutions to capture spatial near and distant dependencies. Apart from that, there is an application of early and late fusions to fuse similar spatio-temporal data as well as the global information. So it predicts the citywide crowd flows and builds a real-time crowd forecasting system called Urbanflow, which is a UI-based thing where uh, looks something like this. So we can see there is heat maps generated based on the grid pattern of the city, and it might not be clearly visible. There is a drop-down option list which shows the local grid area as well as the overall city area, and there is an option of seeing the past data as well as future data. So this is a very nice interface. Uh, so there are three major components in our framework: Mm, online training, online forecasting, and website monitoring. In online training, the collected trajectories from a city are fed into a calculating flows module uh, that outputs two types of flows, namely inflow and outflow. These historical flows are then used to learn the DeepST model in online forecasting. Starting with calculating crowd flows from real-time trajectories, the learned DeepST model is used to predict future flows that are concatenated with real-time flows later. In the last component, in order to monitor intuitively, heat maps are generated from real-time and predicted crowd flows that can show the global status in the city. So, to formulate the problem at hand in terms of DeepST, there is a map region which is divided into M cross N grids, each grid being a region in the city. So now there are many different types of measurement in the region for different spatio-temporal applications, such as we can measure crowd flows, we can measure air quality, bike rent return pattern if it is available in a city. So here the crowd flow has been chosen for this purpose of model. So typically the movement of crowds can be presented by a collection of trajectories. We are naming that as P. So for a grid Mn, uh, the inflow is given by these equations and the outflow, the inflow and outflow is given by these equations. And the problem statement is here, if we know the historical observations, we have to predict the next timestamp future observation. Uh, So now we come to the architecture of DeepST. So DeepST is composed of two components as we have already discussed. So we feed all historical observations into the spatiotemporal component according to the temporal properties. Different timestamps are selected and concatenated together to model closeness, period, and trend respectively. The outputs of closeness, period, and trend are further combined via early fusion, feeding them into a number of convolution layers. In the global component, we first get metadata of predicted time t and transform it into a binary vector, which is then fed into a block that contains one or more fully connected layer. The outputs of the above components are merged via late fusion by the tanh activation function. The predicted tensor at time t is x hat t. Two main activities are being done here. One is getting temporal dependencies. In that, with some temporal domain knowledge and time series properties of closeness, period, and trend, The timestamps bringing higher correlation to each other are selected, thereby reducing the input data size, and then we are getting spatial dependency as well. The convolution operator is used to get spatial dependency. More convolution layers are expected to catch more spatial dependencies. So the closeness period and trend parts are all fed into this similar convolution layer. With convolution, their output are respectively shown by these equations. We have shown what convolution is. So here star is the convolution operator in these equations. F is the ReLU activation function. W and B are parameters of the first input layer, and HC, HP, and HS are output of first convolution layer. So based on fusion time, early and late fusion are done, as we can see here. Sorry, early and late fusion. So early fusion, we employ so to employ this early fusion followed by convolution layer, which is good at fusing similar domains data. The early fusion based convolution can be written as this one, where W and B are parameters actually. Late fusion is adept at fusing different domains data. Meta features can provide some global information such as day of the week meteorological condition, which are always beneficial to predict the crowd flows, air quality, etc. The late fusion can be written as this one, where GT is a meta future vector at T, and HST is output of spatiotemporal component, and WST and WG are parameters. So as shown, the loss function is mean squared error. So here are some baselines and the variations of DeepST models that are used. So it is worth mentioning that DeepST and CNN have similar configurations here. Both each have 4 convolution layers, each having 64 feature maps with 3x3 kernels. The evaluation metric is RMSE. Clearly, the CPTM variant performs the best among all of them. The historical and predicted values are also shown. So so the historical and near predicted values can be used to predict further values in the future, which is referred to as multi-step ahead prediction. The plot here as shown in the slide shows that DeepST is the best result compared to the baselines. Also, the data size was increased to see if there is any effect on the result, and it was seen to have a positive result. So that is about this model DeepST. Thank you.
Future challenges: lack of benchmark dataset. The availability of a wide range of traffic data supported traffic predictions due to the fact that different work use different datasets. It is very hard to access the relative performance of different state-of-the-art models. Difficulty of incorporating external information with traffic data. In traffic prediction, commonly used external information include the weather, accident, event, day of the week, time of the day, and social media data. While the inclusion of the day of the week and time of the day is relatively simple, data that are bound to the specific geographical coordinate or a geographical area is difficult to incorporate with traffic data. Online learning with the widespread installation and traffic loop detector, traffic data will continuously grow in this setting where new data is incrementally added. Traffic trends will shift over time. Using graph-based method to capture special aspect of the data in graph-based method are a promising development of traffic flow prediction because they naturally conform to traffic dynamic. Explore other traffic prediction tasks currently. The Intelligent Transportation System (ITS) field generally focus on the traffic flow prediction, neglecting the other traffic prediction tasks. Lack of up-to-date experimental evaluation. There is a lack of up-to-date and comprehensive experimental evaluation, making it difficult to access how promising these specific ideas are. Experimental evaluation in traffic flow prediction is complex due to two factors. The first one is the lack of benchmark dataset and a problem. The second is the lack of code ability. Applying emerging techniques. These are several emerging techniques that have been applied to the problem of traffic flow prediction. However, as these technologies are still in their infancy, they are much rare compared to more convenient deep neural network structure discussed in previous section. Conclusion. We have explored how the field of traffic flow prediction and had evaluated over the time from classic statistical model to machine learning model and finally to deep neural network model. This critical survey has departed from abundance of contribution dealing with the deep learning technique for road traffic forecasting. The MFCN model considering multiple spec- spectromotor feature and external factor can prevent the model from complex factors shift, achieve the trade-off between the prediction accuracy and specific showing the potential and promising capacity in the traffic flow prediction. The future of traffic flow prediction field lies on determining a more standardized approach that ensures that the significance of recovery every novel idea can be identified. Prediction field will inspire the confidence and eventually widespread implementation of real-time prediction system that can directly contribute to the improvement of the traffic condition worldwide. Thank you.